we saw how French scientist de Broglie provided a major breakthrough. He provided a radical idea that matter has wave like nature. Another radical idea came from from one German scientist, Werner Heisenberg, and this is what we are going to discuss now, the famous Heisenberg's uncertainty principle. This uncertainty principle says that we cannot simultaneously, so it says that simultaneous determination, we cannot simultaneously determine something, and what is that? Simultaneous determination of exact position and exact momentum of a particle is impossible. There are some key words in this statement. First key word is simultaneous. We must, this principle forbids simultaneous, that means at the same time we cannot measure exact position and exact momentum of a particle. The simultaneous determination is impossible. This impossibility does not arise because of a limitation of instrumentation, rather this impossibility is forbidden by nature. This is the fundamental nature of the particles that we see. So, Heisenberg's uncertainty principle is not an outcome of insufficient instrumentation. That means it is not going to happen that in a future time we will get some instrument using which one can exactly locate the position and momentum of a particle simultaneously. This is the fundamental principle of nature. Mathematically, this is given as delta x multiplied by delta p x, which is greater than h by 4 pi. What is this delta x? X is the position of the particle, p x is the momentum of the particle along x direction. This delta x or delta p x are called uncertainty in position, and delta p x is called uncertainty in momentum. Exact determination of position would make delta x as 0, exact determination of momentum will make delta p x as 0. The uncertainty is given by this delta x. Suppose that we have a two-dimensional box within which my electron can move around. If I want to locate this electron with certain amount of precision, the precision, let us say this is my precision. So, I can say that the electron is certainly present in this box, but it is present between this and this. This is what is known as the uncertainty in determining the position. So, we can say where it is, but with an error bar. So, this is given as delta x, and similarly its uncertainty in momentum, and that is delta p x. The multiplication of these two uncertainties is always greater than, or it can minimum be equal to this constant h by 4 pi. H is Planck's constant, and 4 pi is again a constant. So, Heisenberg's uncertainty principle said that you cannot simultaneously measure the exact position and exact momentum of a particle. There has to be a certain amount of uncertainty, and this uncertainty is given in this way. In other words, if you want to measure the position exactly, you must sacrifice the accuracy in terms of momentum, and if you want to exactly measure the momentum of this particle, you must sacrifice the knowledge of the exact position of this particle. You can actually show that the uncertainty of an electron. So, if I want to measure the uncertainty of electron, so I have delta x multiplied by delta p x is greater than h by 4 pi. I can rewrite as momentum. Momentum is, I know, mass into velocity, and mass is if I want to measure the uncertainty of an electron, I would get, I have h, the value of h I know 6.626 into 10 to the power minus 34 joule second, divided by 4 pi mass, which is 9.1 into 10 to the power minus 31 kilogram, which is coming out to be, if you see, something about it is not exact, it is approximately 10 to the power minus 4 meters square per second. All right. We keep this in mind. For uncertainty of an electron is coming out to be 10 to the power minus 4 meters square per second. And then what we let us write this down, uncertainty principle, delta x multiplied delta V x for an electron came out to be 10 to the power minus 4 meter square per second. Let us find out the same delta x delta V x, which is greater than h by 4 pi m, but in this case let us find out when m is 100 gram, an everyday object. In this case, the uncertainty is given as 6.626 to 10 to the power minus 34 joule second, 4 pi mass, which is now 0.1 kilogram. This is 10 to the power minus 1. So, this comes out of the order 10 to the power minus 33 meter square second inverse. So, this is an uncertainty, this is what the uncertainty in position and momentum for an electron, which is 10 to the power minus 4 meter square per second. This is the uncertainty in position and momentum according to Heisenberg's uncertainty principle for an everyday object, like an object which weighs 100 gram, whose mass is 100 gram. So, you can see the uncertainty is extremely small, it is almost negligible for everyday object. So, therefore, uncertainty principle is all right, but it is mostly manifested, or it has severe significance for microscopic particles with very small mass, but for everyday objects, when the mass becomes larger, even in the scale of grams or milligrams, the uncertainty principle can be safely ignored. So, therefore, the uncertainty principle, the corrections that were coming out because of uncertainty principles, they only apply to microscopic world. The macroscopic world, or the world that we see around us, can be safely we can safely ignore the consequence of uncertainty principle into the macroscopic world. We are now adequately equipped to discuss why Bohr's atomic model failed. What was the reason that Bohr's atomic model could not give out all the answers that we wanted? So, let us discuss now the reasons for the failure of Bohr's model. If you remember, the results that were coming out from Bohr's model, we had an analytical expression for Rn, the radius of the orbit. We also had an analytical expression for the speed of an electron in an orbit Vn. So, from Bohr's model, we knew precisely the radius, therefore, we know the location of the electron. We also knew precisely the speed of the electron that is orbiting. So, what Bohr's model said is that it gave exact position and exact momentum, because we knew the mass of the electron and if we know the velocity at the nth orbit. So, we know exact position and exact momentum of the electron in Bohr's model, and this is contrary to what Heisenberg's uncertainty principle suggests. Heisenberg's uncertainty principle tells that you cannot simultaneously measure the position and momentum of a microscopic particle, which is electron in this case. Since Bohr did not know about Heisenberg's uncertainty principle by the time when he was devising this atomic model. So, therefore, Heisenberg's uncertainty principle is not satisfied in Bohr's atomic model, and that is the key reason as to why Bohr's atomic model could not explain all the results. We can now go on to discuss a new branch of theory, which would take into account the knowledge that we get from Heisenberg's uncertainty principle, the de Broglie's hypothesis, and this is what we are going to do next. It is now time for us to take a stock of the things that we have learned so far. So far as the structure of atom is concerned, we have traveled a long way. We started from the hypothesis of John Dalton, which said that atoms are the tiniest indivisible particle. Dalton did not provide any more clarity towards the structure of atom. So, they were simply assumed to be hard spheres. From there, we went to the work of J.J. Thomson, the famous plum pudding model, where now in addition to the atom, there are like positive charges, negative charges were also discussed. In plum pudding model, it was suggested that atom consists of a uniformly distributed positive charge, within which the electrons are embedded. Plum pudding model did an improved job compared to Dalton's atomic theory. However, it was far from the truth. Then we came up with the idea of Rutherford, who established the existence of nucleus. In plum and pudding model, the positive charge was uniformly distributed, that constituted the space of the atom. But now Rutherford's improved atomic model suggested that the positive charge as well as most of the mass, the entire mass of the atom, are concentrated in a very small space in an atom, and he called it as the core, or what we call it as nucleus, and the electrons, they move around the nucleus. But Rutherford's atomic model could not satisfactorily explain why the atoms should be stable, because from Maxwell's theory it was understood that the moving electron should undergo a spiral motion and should collapse on the nucleus, and therefore, the atom should never be stable. We again encountered one more improvement on this theory, that was the work of Niels Bohr, who provided the Bohr's atomic model, where he said that electrons, so again the nucleus are at the center, the electrons move around the nucleus, but they move around the nucleus in fixed paths called orbits, or they are also called stationary states. They have fixed energies. So, that gave us yet another improved version of the atomic structure. However, none of these four models, Dalton's atomic theory, plum pudding model, Rutherford's model, or Niels Bohr's model, none of them could give us the complete picture of atom. While this was the growth in the story of the structure of atom, simultaneously other things were happening in science. For example, it was proved by Max Planck and Einstein that light, which we believe to be a wave, also has particle-like nature. Without that, the black body radiation, the photoelectric effect experiments could not be explained. So, now light has both wave-like nature as well as particle-like nature. Then there was the hypothesis of de Broglie, who suggested that even matter has wave-like nature. So, now light is both wave and particle. Now, the matter that we normally think of as particles are also behaving like wave as well as particle. In addition to that, there was Heisenberg's uncertainty principle, which suggested that you cannot simultaneously determine the position and momentum of a microscopic particle. All these new things actually were very puzzling. We did not know how to take them. The scientists took a stock of the situation. They realized that the Newtonian mechanics served a great deal of purposes. Using Newtonian mechanics, Newton's equation of motion, we could not only discuss or talk about the trajectory of everyday objects, but we also could explain the planetary motion. But when it came to the microscopic world, the electrons, the protons, the subatomic particles, Newton's equation of motion or Newtonian theory failed, and it failed miserably. At that point, there was unanimous agreement that we needed a new theory, a new set of ground rules that will explain the very complicated and very exciting things that were happening at the microscopic world. And this is where the birth of quantum mechanics took place. To begin with, in the year 1926 and 1927, two great scientists, one Austrian, another German. The Austrian scientist Erwin Schrödinger and the German scientist Werner Heisenberg, roughly at the same time, 1926, 1927, around that time, they put forwarded two different versions of quantum mechanics, two different formulations of quantum mechanics. And later on, it was shown that actually both the versions were equally valid. They are essentially one and the same. That is where the formal birth of quantum mechanics took place, and since then quantum mechanics has moved quite a lot. In today's scenario, quantum mechanics plays a very important role in advanced physics, advanced chemistry. I will talk about quantum mechanics, the applications of quantum mechanics in chemistry. I myself, I am a quantum chemist by profession. We normally in the field of chemistry use the principle of quantum mechanics to solve the atomic and molecular structures, and we also derive chemical properties, chemical reactivity of different molecules. We can predict or we can calculate the feasibility of chemical reactions by using the principles of quantum mechanics. And this branch of chemistry which uses quantum mechanics, the principles of quantum mechanics to solve chemistry related problems are called quantum chemistry. Quantum mechanics, being a new theory, required a set of new rules or new postulates that to be formulated. We will first go through two basic postulates of quantum mechanics, on the basis of which we can carry on our discussion further. There are more than two postulates of quantum mechanics, but for our discussion the first two will be sufficient. The first postulate of quantum mechanics tells that there exists something which is called wave function. This wave function is denoted by the Greek letter psi, either in capital or in small, in the small case or in capital case. Quantum mechanics tells us that there exists this, for every quantum mechanical system, there exists this wave function which is denoted as psi, that contains all the information that we need to have. Everything that we need to know about a system is present in this wave function. This wave function can be a simple function let us say it can be as simple as a function like x or x square or sin x or e to the power minus x. It can be real or it can be complex, it can be e to the power minus x, or it can be a plus I b, or it can be combination of one or many of these functions. It can be as simple as this wave function, or it can be extremely complex that I even cannot begin to start writing. If I have a system where there is one electron, the wave function will contain all the information about this single electron, its position, its momentum, and so on, so its energy, and so on and so forth. If I have, let us say, 100 or 1000 number of electrons, then also this wave function will contain all the information about the entire system, which now consists of 100 or 1000 electrons. So therefore, you can imagine if I have 10 to the power 3 number of electrons, then this wave function will contain the information about the position of each of these electrons. So this wave function can become very complex, or it can also be very simple. So we do not know, or we need not define the wave function at the moment. So what, for our discussion, it is sufficient to appreciate the fact that for every quantum mechanical system, by that I mean it could be an atom, or it could be a molecule, it could be a cluster, it does not matter. For every quantum mechanical system, there exists a wave function. What physical picture does this wave function give? Actually none. The wave function does not have any physical meaning. This wave function does not have, it has got no physical meaning, because it does not have to be. It does not have to carry a physical meaning. This is a complex mathematical construct, a mathematical function that contains all the information. It does not have any physical meaning. However, Max Born, the German physicist, suggested that although the wave function itself does not have a physical meaning, what has a physical meaning is this psi mod square. This has got a physical meaning. And what is the physical meaning of this psi square? This is nothing but the probability of finding a particle, in our case it will be an electron, at a given point in space. So the wave function itself does not have any meaning. However, the mod square of this wave function psi square has got a physical meaning, and it means that what is the probability of finding an electron at any given point in this in space. So if an electron which is going around the atom, if I know the wave function, I know psi square, and therefore I know at any point around the nucleus what is the chances that I can find this electron that I am interested in. Now, since it signifies a probability, therefore it cannot be negative. It is always a positive quantity. So let us see a few examples. This psi mod square actually has a special meaning. For example, if my wave function is x, then psi square is easy, it is x square. If my wave function is e to the power minus x, psi square is e to the power minus 2x. However, please note, when my wave function is a complex, this psi square has this meaning. Actually, psi square should be written like this, psi star, which is actually the complex conjugate of psi multiplied by psi. As long as your function is real, like x, x square sin x, or e to the power minus x, it does not matter, we do not have to write in this format. But if your function is complex like this a plus I b, then I must find out the complex conjugate of a plus I b, so which is a minus I b and a plus I b, and this gives me a square plus b square. Remember, this definition is necessary because Max Born suggested that psi square has a physical meaning, and this physical meaning is that it is the probability of finding an electron at a given point in space. So, since it signifies a probability, therefore, it must be always a real number, it must be it must always be a carry a positive value. All right. We saw the first postulate of quantum mechanics, which says that there exists something called wave function, which contains all the information. That is nice, because wave function contains all the information, that is very good. But you would ask me this question, that how will I get this wave function? How would I get some information that I want to know about the system starting from this wave function? That is given by the second postulate. This is what we are going to discuss next. The second postulate says that it talks about how we can get information from this wave function. The wave function contains everything, all the information, but how will I get this wave information from this wave function? This is what we are going to discuss next. Now, quantum mechanics has the following recipe for this. It says that for every observable that you want to see or you want to know, you can think of doing an experiment and getting a result out of it. For every observable, there exists an operator. So, it defines, with the second postulate, it defines that there exists an operator for every observable. What is an operator? An operator can be as simple as like this, and this is an addition operator. It can be a subtraction operator, it can be a square root operator, it can be a square operator, it can even be a differential operator, or it can be an integration, or it can be a logarithmic function. So, these are different operators. You know that if I apply this operator, let us say this operator is square root. If I apply this operator on a function, now it is 9, then I know it will give me a different value, it will give me a result, that is 3. If I use this operator on again the same 9, I will get a different value at 81. If I use, let us say, this operator on a function a x, I will get a. So, an operator is something, it is a rule that applies to a function. Now, what second postulate of quantum mechanics tells is that every observable corresponds to an operator. What observables can we have? Let us say we want to know about the position of the particle, position of the electron, all right. So, there must be an operator for that. So, we normally signify an operator as a hat, with a hat on top of it. So, position operator, I call it x operator. I may want to know about the momentum of my electron, all right. So, I have got a momentum operator. I may want to know about the energy of the system, all right. The energy is associated with an operator which is called Hamiltonian. It is named after British scientist Hamilton. This is called Hamiltonian. This is H with a hat on top of it. So, you do not have to worry about the form of this operator, or this operator. In later class, you would actually get to know how to construct an operator, but for the moment, for the time being, it is sufficient if we appreciate that there exists an operator for every observable that we may want to know. If we want to know about energy, there is Hamiltonian operator. If you want to know about momentum, there is momentum operator, and so forth, so forth. All right. So, I have now defined, I got to know something about this wave function psi, I got to know that there exists an operator, but how would I get this information? So far what I said is that for energy there is an operator Hamiltonian, but how would I get that? This is what will be done next. Let us say I want to know about the energy of my system. So, quantum mechanics tells that there exists this wave function psi, there exists this operator h. So, wave function contains all the information, operator asks the question, operator. Now, this time since I am trying to get energy, I am using Hamiltonian operator. Using this Hamiltonian operator, I will ask the question to this wave function, which is the citadel of all the information. And when I ask the question to this wave function using my Hamiltonian operator, the answer that I will get will be energy. So, this is the wave function which contains all the information. This is the operator that I am interested in to get an idea about that particular observable. In this case, I am interested in getting energy. So, I apply this operator on this function, I get the result. So, this is the place for my result, and in this case this is the energy, this is my wave function, and this is the Hamiltonian operator, Hamiltonian operator. And this equation that you see here, H psi equals E psi, is a very simple equation to write, but one of the most difficult equations to solve, and this equation is called as Schrodinger equation. You see that there are two dots on top of O. This is called O umlaut, and it is pronounced as if it is OE. So, SCHROE, Schrodinger. This equation was given by the Austrian physicist Schrodinger, and this equation is Schrodinger equation. Now, to be able to get the energy of my atom, I would solve this Schrodinger equation, which is H psi E psi. What is known? What do I know? I actually know only the Hamiltonian here, because Hamiltonian is the energy operator. If I am asking a question, I know the ingredients of the question, but what I do not know is the answer. So, I do not know wave function. So, here unknowns are wave function psi and energy, and known to solve this equation, known is the Hamiltonian, the operator. I know the operator, and what I want to know is what is the wave function and what is the corresponding energy. Let us see. So, this is, there are several tricks to solve this equation. We will not talk about any tricks as to how to solve this equation. We saw that we have to solve Schrodinger equation, which is H psi equals E psi, to get idea or to get information about any quantum mechanical system. If we are interested in solving hydrogen atom, so we must construct the Hamiltonian operator corresponding to hydrogen atom, and then solve Schrodinger equation, and that the solution will give us wave function psi and the corresponding energies E. Now, we will discuss about what solutions we get when we solve the Schrodinger equation of hydrogen atom. Next, we are discussing the results from the solution of Schrodinger equation. We are not going to discuss how to solve them, but we will use the results and discuss what we can learn about this. When you solve this, this is the Schrodinger equation, H psi equals E psi. First outcome of it is that we get a series of wave functions. So, actually we do not get one value of psi, we get a series of like quite a lot. It depends on how we did the calculations, but it forms the so called complete set of wave functions. There are many wave functions available. So, we get a series of wave functions and we call them orbitals, or even equivalently atomic orbitals. These orbitals are different from orbits that we saw in Bohr's atomic model. Orbits were fixed path around which the electron was going around in Bohr's atomic model. Orbitals are the solution or the wave functions obtained from solving Schrodinger equations. And these are also called atomic orbitals, and these orbitals actually give us the address of electrons. As you know, according to Max Born's hypothesis, that square of the wave function psi square represent the probability density of finding the electron at any point. So, therefore, wave function therefore contains the information quote and unquote address of electron, how to find the electron or where to find the electron. In addition to this, we also get a series of energies. Each energy corresponds to one value of wave function. So, as I said, I have a series of wave function and each wave function corresponds to one value of energy. So, therefore, I have got a series of energies, and these energies are actually they form a discrete set. So, they have certain values like 0, 5, 10, 15 like this, or some other it can be a real number. I am just trying to say that it is not that 0, 1, 2, 3, 4, 5 everything is present. It could be 0, 5, 10, 15 or 0 or 10, 16, 29, it does not matter, but these are discrete values. This is not a continuous values. So, I get what I get. I cannot say that energy this is the result that I am getting, these are the energies, then I cannot say that I have energy 1, because I do not. I only have 0, 10, 16, 29. So, they form a discrete set. Right. Now, first we will discuss about the orbitals, and then we will come to talk about the energies. The first topic of our discussion is the atomic orbitals that we get from solving Schrodinger's equation. Let us talk about orbitals. These orbitals, which are also the wave functions, they tell us about the size, shape or orientation. As I said, orbital is the address of electron. So, this is the orbitals actually tell us how is electron's house, what is its shape, what is its orientation. So, we will talk about the orbitals, and then we will see where in which kind of place the electron lives. All right. Since I said there are so many orbitals which are coming out from the solution of Schrodinger equation. So, we must be able to identify uniquely an orbital from its size, shape and orientation. So, the next target is unique identification of an orbital. How do I do that? To be able to uniquely identify an orbital, I require 4 sets of information. These are called quantum numbers. First is called principal quantum number. Second, azimuthal quantum number. Third is magnetic quantum number, and fourth is spin quantum number. Principal quantum number is often signified with n. Azimuthal quantum number is given as L, magnetic quantum number m, spin quantum number ms. These are the 4 quantum numbers that we require to uniquely identify an orbital. We will now discuss about each quantum number and what kind of information does it give about the orbital. This is what we will discuss next. First is our principal quantum number. Principal quantum number, which is given by the letter n, it tells us about the size of the orbital. It is like how big the house of electron is. This is the size of the orbital, whether it is a big orbital or it is a small orbital, the house is big or small, this is what it gives us. And to a large extent it also decides, this principal quantum number also decides the energy of the orbital, but we will come to that in a moment's time. The values of these quantum numbers n can be 1, 2, 3, 4, any integer value, it can go on. When a larger n we have, if the quantum number n is a large number, it simply indicates that the electron, this orbital of this electron is very large. That means, what does that mean? If this is the nucleus and we know that electron is going around the nucleus, if n is large, that means the distance between the electron and the nucleus is very large. That means, the orbit, the house of this electron, when it occupies the principal quantum number n, it is also large and it is found far away from the nucleus. So, n equals 1 means the electron is closer to nucleus, n equals 2 it is little farther, n equals 3 it is farther, n equals 4 and 5 and so 6, it goes on like that. So, n equals 1, 2, 3, 4, 5, these are different values. There are also have a different name, we also call them, signify them as shell. When n equals 1, we call that as K shell, when n is 2, we call it L shell, when n is 3, we call it M shell, N shell and so on and so forth. So, this is about the principal quantum number n, which talks about the size of the orbital, which also translates to the energy of the orbital, and it tells that if the principal quantum number n is large, that means the electron is found farther from the nucleus. The next quantum number is azimuthal quantum number. It is also called orbital quantum number, and given the letter L. If principal quantum number talked about the size of the orbital, azimuthal quantum number talks about the shape of the orbital. So, we saw how big was the size of the house of electron. Now, with orbital angular momentum, we will see that what is the shape of the house of the electron or the shape of the orbit. This orbital quantum number or azimuthal quantum number L can be from 0, it can be 0, 1, 2, any number up to the value of n. Actually, the value of principal quantum number n determines the value of L. If n is 1, that is the K shell, if the principal quantum number n is 1, then we have got only one possible value. So, the possible values of L are determined by n, but it actually please excuse me, it goes from 0 to n minus 1. So, I will take this example. If n is 1, then how many what are the possible values of L? So, L can be only one value, that is 1 minus 1, 0. If n is 2, what are the possible values of L? L can be 0 or it can be 1, because it can go up to 0 to n minus 1, and since n is 2, therefore, L can be 0 or 1. If n is 3, L can be 0 or 1 or 2 and so on and so forth. So, the values of L can be from 0 to n minus 1. So, therefore, for a given principal quantum number n, how many L values are possible? That is, the number of possible L values is given by n, because you always have 0 and then until n minus 1. So, therefore, the number of possible L values is n. So, in this case number of L values is 1, in this case number of L values is 2, in this case number of L values are 3, and these values are 0, 1 or 2. So, we saw that the orbital quantum number L is determined by the principal quantum number. So, principal quantum number is fixed, and then principal quantum number decides what are the allowed values of this orbital quantum number or azimuthal quantum number, and it goes from 0 till n minus 1. Now, we see that here L value is 0, here again L value is 0 when n is 2, again here also when n is 3 there is a possibility of L value of 0. Simultaneously, we can see that when n is 2 we have one possibility of L equals 1, and here when n is 3 then also we have an orbital where L value is 1. Is there a similarity between the 0 value of L when n is 1 or n is 2 or n is 3? The answer is yes, because orbitals, as I said, they determine the shape of the the orbital quantum number determines the shape of the orbital. This is what we would discuss now. When L is 0, we saw that L can be 0 or can be 1 or can be 2 or any other number. When L is 0, the shape of the orbital is sphere, is just a sphere, right. And we identify this with a shorthand notation as small case s. When L is 1, the shape of this orbital, when the azimuthal quantum number L is 1, the shape of this orbital appears to be like a dumbbell. So, dumbbell you would perhaps know that it has got 2 lobes. So, this is what the shape of the p orbital the orbital that has L equals 1 look like. So, it has got 2 lobes on 2 sides, and we signify that with small case p. L equals 2, it has got 2 dumbbells. So, you can have one dumbbell like this and another dumbbell like this. So, these are the general shapes of the orbitals, and we call this when L is 2, we call these orbitals as d. So, when L is 0, the orbital is spherical in shape called S. When L is 1, the orbital is dumbbell in shape, we call P. When L is 2, it has got 2 dumbbells, and we call the shorthand notation for this is d. Now, let us go back to the previous exercise that we are doing, but that we saw that when n is 1, L is 0. So, how can we identify this orbital? We can say that okay, n is 1 and L is 0. So, we can identify this orbital as in the following way. So, we say that okay, this is the value of n, and then we use the shorthand notation of the orbital shape. When L is 0, we call it as S. So, we call this orbital as 1s. When n is 2, L and L is 0. So, we see that n is 2. So, we first write it 2, and then we write the shape of the orbital, we call it 2s. For n is 3 and L is 0, we write this orbital as 3s. Similarly, when n is 2 and L is 1, we give the value of n here 2, and then we check what do we call when L is 1, we call it p. So, we will call this orbital as 2p, that means its principal quantum number is 2, its azimuthal quantum number is 1, that is why we are calling it p. And similarly, when n is 3 and L is 1, we call this as 3p, principal quantum number is 3, azimuthal quantum number is 1, and when principal quantum number is 3 and azimuthal quantum number is 2, we say the orbital as 3, which is the principal quantum number, and when L is 2, this is called as d. So, we can go on this way. So, you would need to know actually what happens L equals 3. It has got very complicated shape, I cannot draw them, we call them f, and it goes on further S, P, D, F, G and so on and so forth. So, this way we saw that the principal quantum number talked about the size of the orbital, azimuthal quantum number talked about the shape of the orbital, whether it is spherical, dumbbell, double dumbbell or complex. So, if n was called as shell, these L values they represented what we will call as subshell. So, n is shell, L is subshell, n can be 1, 2, 3, 4, 5, L goes from 0, 1, 2, 3, 4 until n minus 1. We saw the two principal quantum numbers, we discussed about them, the principal and azimuthal quantum number, and we will continue our discussion on the quantum numbers in our next class, when we will talk about the other quantum numbers and what other features they will bring into the structure of atom. Thank you.